Hello everyone, and welcome to my first neural computing tutorial. We're going to be solving a simple perceptron question, where we're given a pair of outputs, and we need to find a corresponding pair of input vectors. I'd recommend not trying to tackle this question, unless you know the basics of vectors. Let's take a look at the information that's given to us. We know that the output O of this perceptron is equal to the weight associated with the perceptron transposed times the input vector, all put into a function f. We're given the means to find the weight, and we're given the function f. We're also given a pair of outputs, for which we need to find the corresponding input vectors. These outputs are both equal, and the input vectors need to be orthonormal, so they need to be orthogonal unit vectors. Now, to start with, let's give I1 and I2 some variables to make things easier. So let's say I1 is x, y, and z. And please excuse the writing. I'm using a mouse because I don't have a suitable camera to record my paper. And let's say that I2 is equal to L, M, and N. Right, let's just fix this N a little bit. It looks a bit too much like a H. Okay. Let's work out the weight next. So we're given Wn is equal to n minus 2 cubed, where n is from 1 to 3. What this means is that each row of the weight is equal to the number of the row, so row 1, 2, and 3, where the number is n. We get the number of the row minus 2 cubed. So, for instance, you can easily work this out. The first row is 1 minus 2 cubed, which is minus 1 cubed, so just minus 1. The second one is 2 minus 2 cubed, which is 0 cubed, and just 0. The third one is 3 minus 2 cubed, which is just 1 cubed, which is just 1, once again. So next, what can we do? Well, let's work out this part here that we're passing to the function f. We need to get the weight transposed. All we need to do here to transpose this is topple it onto its side. So it's a row vector instead of a column vector. So Wt, the weight transposed, is equal to minus 1, 0, 1. And then Wt times I, well, let's start with I1. Wt times I is equal to minus 1 x, 0 y, plus 1 z. So it's just minus x plus nothing for y, plus z at z. Okay, this is what we've got for our x value that's going to be input into this function. But before we substitute this for x, let's work backwards from the outputs, from one of the outputs. They're both the same anyway. And let's get a rough idea of what x needs to be. So we've got 2 plus e, where e is the exponential, by the way, for those of you that don't know, it's a constant. 1 minus x cubed is equal to 27 for both of the outputs. Well, if we just cube root this and cancel that out, we get 3. So we have 2 plus e to the power of 1 minus x is equal to 3. What this means is, well, let's put these arrows here first. Okay, what this means is, well, e 1 minus x is equal to 3 minus 2, which is just 1. Now for e to any power to be equal to 1, what can that power possibly be? It can only be 0, because anything to the power of 0 is 1. So we know that 1 minus x has to be 0, is equal to 0. And then from this, we get x is equal to 1. Well, let's substitute in this minus x plus z now, in which case we get minus x plus z is equal to 1. Okay, well, what's I2 going to be? This exact same thing for I2 is just going to work in the exact same way, because I2 has the same output, and we're just going to put it through the exact same process that we put I1 through. So all I2 is going to be, so for I2, all this is going to be is minus L, because L corresponds with x, plus n, because n corresponds with z. That is equal to 1. And we're also told that these vectors are orthogonal. Let's not worry about the unit part for now. Let's just focus on the orthogonal bit. Well, what does this mean? It means that the dot product of I1 and I2 has to be 0. The dot product, as you should know, is just going to be xl plus ym plus zn. So xl plus ym plus zn is equal to 0. Okay, this is I1 dot I2. It's the dot product. Okay, so we have 3 equations now. We don't need to do anything fancy with these. We just need to find an I1 and I2 that are orthonormal and lead to this output. So let's just try, for instance. Let's let x be 0, let's let z be 1, and then let's let L be minus 1, let's let n be 0. What would this give us? Well, if x is 1, if x is 0, L is minus 1. These are both let's just let them both be 0, regardless. We have z as 1. And by the way, if x is 0 and z is 1, then 0 plus 1 is 1. If L is minus 1 and n is 0, minus 1 plus 0, minus 1 even, plus 0 is equal to 1. And then n is just 0. Well, this, of course, outputs 0, because 0 times minus 1 plus 0 plus 1 times 0 is just 0. Well, in this case, let's write out I1. I1 is 0, 0, 1. I2 is minus 1, 0, 0. Well, does this work? Do these vectors lead to an output 27? Let's test I1 first. If we do the weight transpose times I1, we're going to get 0 times minus 1, 0 times 0, and 1 times 1. I'm going to add those all together. Well, we obviously get 0 plus 1 times 1, which is just 1. What is f1? f1. Well, that is equal to 2 plus, let's just put a line here, 2 plus e to the power of 1 minus 1 cubed. Well, that is equal to 2 plus e to the power of 0, which is just 1, cubed, which is equal to 3 cubed, which is 27. So f1 does give us the correct result. What about I2? Well, I2 is minus 1 times 1, minus 1 times minus 1, which is 1, plus 0 times 0, plus 0 times 1. Again, we're going to get f1, aren't we? So again, it's going to give us 27. And since both O1 and O2 need to be 27, these are both correct results. Well, what about them being unit vectors? Well, as you can see, they're already unit vectors. They're already of length 1, because it's just 0, 0, 1, and minus 1, 0, 0. Normally, we'd need to calculate the magnitude and divide each component of the vector by the magnitude to make this into a unit vector. But in this case, we don't need to do that. So our answer is just I1 is equal to 0, 0, 1, and I2 is equal to minus 1, 0, 0. Okay, I hope you enjoyed this video, and I hope it helped you learn more about working with perceptrons. Thank you for watching, and I'll see you next time.